Mic check.
How's it going, everyone? Cool. We lost our moderator just because they had an appointment and we're running a little bit behind schedule here. So Barna and I are going to moderate our own fireside chat. I guess just taking a look at the questions here. Barna and the Malda team are doing some really cool stuff with ZK and DeFi, or what we coined a new term. It's ZeFi. And yeah, I think like the work that they're doing really is worth celebrating and talking about in a little bit more detail. Meanwhile, we're building a protocol called Boundless. Just sort of creates an abundant supply of zero knowledge proofs through a decentralized protocol. And you can kind of think of it as like the modular ZK prover for any chain. And yeah, we're excited to talk to you guys a little bit about that. So I think the first question that we had here was like, what is the universal ledger? And this is for Barna, and your vision for DeFi.
Yeah, so our vision for DeFi is simply to have the same application serve the same quality of service on different rollups. Is my mic working? Can you guys? Yeah. So essentially, we have the scaling roadmap on Ethereum. There is a bunch of layer 2s launching right now. In my opinion, they will be not so many in the future, like 3 to 5, but you still want to have a trustless interop, which in my opinion, it's only possible via ZK right now. And you want to have contracts for DeFi protocols that work on multiple chains. I think it's important to shift the bridging space into B2B and have protocols rebalance based on these market conditions to serve everyone with the same quality of service. And what I mean by that is if you think about it like large lending protocols that are existing, they have a different quality of service on mainnet than, let's say, on a rollup like Arbitrum. They have infinitely deeper liquidity depths. But if you are able to serve the orders globally, the user experience improves, and we are bringing huge scaling opportunity for the rollup ecosystem as well, because there will be more investments. People will not miss the investments based on time-based opportunities, and that we think will just work very nicely.
That's awesome. And I know you guys used our zkVM in particular to build an interoperability solution. I guess I'm curious, just sort of like how does that work in Malda? And I guess as a second question, why didn't you guys just use something like Intense, or why did you take this particular approach for cross-chain lending and interoperability in your protocol?
Yeah, that's a good question. So let me go through how they work. They work very simply. We're generating state proofs on the different rollups, and then we update the universal ledger, which we store only on Linea based on those zero knowledge proofs. And we are also generating proofs when you are trying to borrow or withdraw. That is a state proof on Linea. And against that proof with some additional verification, like you want to wait like a couple of blocks to make sure there are no reorgs, you can also withdraw your funds or borrow against it. And the reason that we saw that this is a more optimal solution than Intense is because we don't want to have constant transfers for the users. And with this design, we are still using intent-based bridges. That's our preferred method of choice to transfer the funds between our pools on the rollups, but we can just absorb and aggregate a huge amount of the order flow. So lending protocol is quite optimal for this, and then we can do like a daily rebalances, and then for the users it's much better. While if we would like use Intense and transfer the funds from here and there on every user, I think that's a suboptimal solution, and we are trying to build something very optimal.
Yeah, that makes sense. So the assets stay on the original deposit chain, right? And so you're not actually transferring back and forth all the time.
Yes, they stay on the deposit chain, and like daily we just take a look at like what is the expected demand on the given chains, and based on that we rebalance. And then there will be another component which we have not added yet, which will be an on-demand rebalance. And actually we are thinking to leverage like Intense there as an optimal way when a user wants to have like a large order. Let's say like there is 100 million USDC in the whole protocol and they want to borrow all of it for some reason, and the intents can be very useful there because they only want to borrow if the transaction goes through, so they don't want to send a transaction that fails. And with the ZK proof, they could generate the transaction, but then we would need to transmit this ZK proof on every chain. And for example, there I think intents are more optimal, but underlying logic, zkVM is more optimal, I think, to be used as an interop solution.
That's great. I guess if we had a third moderator, they're supposed to ask me a question about what Boundless is. So I'll tell you guys.
I can ask you.
Yeah, go ahead. Go ahead.
Yeah, so Brett, can you describe Boundless? How does this tech solve DeFi's guessworks and limitations compared to traditional solutions? And then I want to add a personal question. How do you implement all the feedback that you get from your partners that are building on Boundless?
That's a great question. I like that. You're going to have to tell me how we're doing at that. But
I think you're doing good.
Okay, cool. Yeah, so what is Boundless, I guess, is the first question. I think everybody recognizes the power of ZK when it comes to blockchains, both for DeFi applications like Malda, and then also for rollups and native rollups, based rollups eventually. Even on Solana and ecosystems like that, right, with network extensions and sort of their embracing of the separation or like the modularization of execution. Obviously, Celestia did a great job, sort of perpetuating this idea of modular blockchains. We have modular DA, modular settlement, and there really aren't modular execution protocols that are focused just on making sure there's sort of a robust supply of these zero-knowledge proofs. So if the adoption of ZK continues to increase in the way that it is, there's going to be orders of magnitude more demand for zero-knowledge proofs than there are today. There's already pretty significant demand just in terms of zero-knowledge rollups. That's where most of the demand comes from. But DeFi projects are adopting ZK, like Malda, Tokamaks using our zkVM, Eigenlayers using our zkVM to enforce and enable slashing. And then interoperability solutions as well. So, bridging teams like Union Protocols are using ZK in deep ways. And then even like, the wormholes and layer zeros of the world will likely sort of take the ZK-based interoperability approach where you're generating, ZK light client proofs of the consensus of a given chain on both ends of an exchange and really increasing the security of the interoperability protocols that we rely on to something better than a multi-sig, which is where we've been stuck for quite a while. So just lots of demand for zero-knowledge proofs. And you can just think of Boundless, the protocol that we're building, as the modular ZK execution layer for any chain. So whether you're a DeFi project on some chain or you're a layer 2 itself, we've built this off-chain node implementation that allows provers to connect hundreds of GPUs into a single instance of the node and really facilitate a market for these requests for proofs. You can think of these requests for proofs as kind of like paying for gas or block space on Ethereum, except in Boundless, you're sort of, it scales perfectly horizontally. So more provers you have, the more ZK execution capacity that the network has. Boundless is not a blockchain. That's the interesting part. It's more like Chainlink, where it's a set of off-chain infrastructure and then a set of on-chain smart contracts. And we rely on these settlement chains, as I would describe them, like Ethereum or Layer 2. We rely on their consensus to facilitate the market. So that way a rollup, since we built this in an off-chain way, that way a rollup doesn't have to rely on a second rollup to sort of make its own proof supply chain. Espresso is like a good example. It's like a shared sequencer, and I think it makes sense for sequencing maybe to rely on this other chain, but you ideally don't build a blockchain with a dependency on another one. And so we built it in a really lightweight way that didn't necessitate a rollup or DeFi application like Malda to depend on a new layer 1 or a new layer 2. We think those dependencies can get kind of ugly. So that's kind of what Boundless is, and you can think of it as, since zero-knowledge proofs can really execute and provide verifiable execution for any chain. A good example is like Eclipse is using zkVMs for their ZK fraud proofs. And so you can run the SVM in a zkVM. Obviously, there's lots of teams that are running, generating proofs of EVM execution. So like ZK EVMs inside of a zkVM. A good example of that is like Tycho. They use our zkVM as well as SP1. And so you can see that. And then even like MoveVM, you can run that in our zkVM if you wanted to generate sort of a proof of that execution. So zkVMs provide this really general environment for execution across chains. And that's how you can kind of think of it as a solution to the gas problem. Whereas in Boundless, when you add a prover, the capacity of the ZK of your verifiable execution goes up. If you add a node in Ethereum or any consensus-based chain, for example, you don't get more throughput, right? The block size doesn't change when you add a node. In fact, now you have an additional node that you have to achieve consensus within the block time. So it can actually sort of slow the chain down. So that's why we called it boundless. Number one, there's no limits on the execution size. So you can run a proof really in perpetuity, some really giant long, for example, somebody's doing what is it called? Stochastic analysis in the zkVM. Linear regressions are really easy, but you can even get much more sophisticated in your logic. And so I think that's the way is like we kind of break the block size limit is the way that we think about it. In Eigenlayer's case, for example, they're generating proofs that are 1.2 billion gas, only cost about $10. You can never get those to run on the Ethereum layer 1. And so, yeah, that's what we're doing. I guess the other question, as I just took like way too much time explaining what Boundless is. And I think I covered it all.
Yeah, I think I just want to advance thing like what I like about Boundless is that you don't have like the constraints of solidity, right? That's a huge value proposition right there. Like you can create an application basically in Rust and then just use the proof to verify it. That's kind of the future, the way I see it.
That's an important part. Like we as an industry are dying for real world users. And in order to have more users, we need real world applications that solve real problems for people.
Also devs. You can onboard more devs with Rust.
Exactly. And like we need devs. Devs need to be able to write more expressive logic, build more complex applications without constantly playing gas golf and reducing everything to a game of token exchanges. And so that's what I personally am also very excited about is you're not limited to solidity. There's no gas limit. There's no transaction size limit. You can really think of ZK as like a serverless function for smart contracts. Normally today you write a smart contract and they're called successively, sort of end to end. And really like ZK gives you this async capability where your smart contract can actually call for some arbitrary off-chain computation that would be way too expensive to run on the chain. And so if you think about the way traditional software is built and how much we rely on serverless functions, Lambda functions, microservices, databases, and other APIs, really smart contracts will get these capabilities more like traditional software through ZK and Boundless. I guess I think that so in Malda's case, the question is like what real world DeFi applications benefit most from these capabilities? And I guess, do you have a specific example?
I actually have a very specific example. So we still have like this mix of ZK rollups and optimistic rollups, right? And there are for real world applications, you probably want to deploy it on a ZK rollup, like a payment system, like with a debit card. This MetaMask is doing, for example, they decided to only deploy it on Linea, right? So I think there will be other examples and use cases, and I think those applications can leverage to access liquidity from a different chain. And it also, even if everything turns to a ZK rollup, it might make sense for them to not create a multi-chain architecture, but still get all the users and a money market like that. It can be leveraged that way, as the users can just specifically go to Linea and for example, borrow funds that they will be using for payments, or it can be another chain, right? Or it can be something on Ethereum mainnet. There are probably an abundance of examples, and I really am interested to see more of these. What about you on Boundless? What real world applications?
Favorite applications of Boundless? I mean, besides Malda, of course, which is like a great example. I think there's again when you want to achieve, let's just say like stick with this theme of real world applications. You really need access. Ideally, you wouldn't be limited or have to pay for access to data. So today, for example, like you go to query the state, like the token balance of for an ERC20 token or something like that. You have to pay for an S-load operation on the EVM. It's like 3,000 gas. That's not that expensive, right? But that just assumes you only want to check one token balance. If you want to build a really like sort of data-rich application, and for example, query the state of 1 million accounts in your Solidity contract, you're talking about, what is that? I don't know. Somebody do 1 million times 3,000. It's billions and billions of gas, right? So I think that's like about 3 billion gas. And that's like completely economically infeasible today on the Ethereum blockchain. And so your ability to do really sophisticated, and honestly, that's not even that sophisticated. Think about in the normal applications in the Web 2 space, you're calculating over billions of data points, potentially terabytes of data, et cetera. And so it's just so expensive even to just do a fairly basic query in a traditional software development context. And so, yeah, one of the things I'm most excited about is actually this library called Steel that we built. It's a really powerful tool for DeFi applications. And it lets you generate historical state proofs for Ethereum. So you can off-chain in a zkVM query an RPC for the state of 1 million accounts. We can generate a proof of the state of those 1 million accounts. We can then compute over that state. So, we can do a linear regression or some stochastic analysis, whatever it is that you need to do with that data. And because we're doing this off-chain in zk, the cost of execution is about 1/1000th of the cost as if you were doing this on-chain. If you're quite clever, you're like, okay, but how do you trust that you're computing over the correct state in a Steel contract like this or a Steel program like this? And in Steel, we actually make a commitment to valid blocks. So like if we're using Ethereum as an example, we can query thousands or millions of contracts and their state, calculate over that, and then we commit to which block we queried that data from. And at the time we verify the proof, we double check that that is in fact a valid block. And so you get full validity proof guarantees. There's no trust in these solutions as long as the proof system itself is sound and free of bugs. There's no optimistic solution required. There's no multi-sig required. These are full validity proofs. So that's something that really excites me about zk and DeFi and what Boundless can help unlock.
Yeah. Yeah, let's talk about the challenges and solutions, right? So our experience building on Boundless with the zkVM for Malda, it's a long journey. Good development takes time, and I think maybe I don't feel like we face many hurdles, right? Because we are bothering the team all the time with questions, and they are patient enough to answer it, which is very helpful. But I think like main hurdles that we were facing was to understand like how to verify the state of a layer 2 on another layer 2, which is something that you guys are actually building into Steel as well. I know, but we didn't have that during our development, so we had to custom build it. That was potentially like one of the hurdles, but otherwise building with Steel was pretty straightforward. You have just a bunch of stuff available in Rust. You have light clients that are available in Rust that you can leverage for this purpose. So I don't really have any other hurdles.
I'm going to remind Barna of some of the hurdles that they had. he's a very optimistic gentleman, so he doesn't seem to remember them. But there definitely are some. So like Steel is cool because normally when you're building zk protocols, like historically you had to write zk circuits. Those are often written in Rust or a language like Rust or a DSL like Circom, which Jordy, who was on stage a little while ago, and their team just have built this amazing technology that we're building all on top of. But in the zkVM, you just write generic Rust traditionally. And what's cool about Steel is you can actually call Solidity contracts in it. So you can give a Solidity contract address. We can go fetch that contract from an RPC, ABI decode it, and we can just actually execute that contract directly in the zkVM. So that makes it pretty accessible for developers who know Solidity. You do have to know Rust, and I think Barna and his team are very capable, and they've been able to handle the Rust component. There's like Rust glue code that sort of goes around that. Let's see, challenges. I think when you guys are programming, like Barna just mentioned, like how do we sort of prove the state of an L2 through the L1? What does that look like? Because ZK, you can be so expressive. You can do things like, say, generate a proof that the state root of OP chain or of Arbitrum or of Linea contains a particular transaction. And that's exactly what they're doing. So they're saying like, hey, yes, somebody deposited on this L2. Now I have the L1 state root, which is really just like, you can think of it like a hash. And the sort of software engineering sort of knowledge necessary to sort of take that hash, decompress it, prove that an actual transaction was included in that is a little bit different than just writing a Solidity contract, for example. And so there are definitely some hurdles that are necessary for software development teams, particularly if you're usually building apps and dApps in just like Solidity and TypeScript or React, for example. There's definitely some hurdles there. I think another one was certainly, and we've come a really long way, but was proving performance and cost. So like early on, our zkVM didn't have support for a number of precompiles that Barna and his team needed. And a precompile on a zkVM is like, imagine that there's some bottleneck in your performance. You're doing some operation over and over again. Like you do lots of catch-up caching, when you're doing EVM stuff, for example. And so we had to write some dedicated ZK circuits just to sort of remove those bottlenecks from and sort of get to an optimal latency and acceptable performance for Barna and his team. And just in terms of zkVM performance, it's just come so far. We built the first type 1 zkEVM called Zeth in, I think it was August of 2023. And at the time, we're like, this is so cool. You can use a general purpose zkVM to prove Ethereum blocks. And then we were kind of like, oh crap, it'll cost $170 million a year to run this on Ethereum mainnet. So like performance was like way too slow, way too expensive. And we've sort of just been obsessed with performance since then. I think we're at somewhere around a 680x performance improvement since then. So the last I checked in last November, it was under $500,000 now for us to prove all of Ethereum mainnet in our zkVM. So we went from 170 million in August of 2023. Now we're well under 500,000, and we've doubled performance since I last run those numbers. So, you know, we're somewhere around 600 times more performant than then. So yeah, just kind of keep trying to make things faster and more efficient. There's other zkVM teams that are doing great work in this area as well, and that'll continue to make new use cases more and more feasible.
Yeah, definitely proving times, improving performance. It's the most important part for all the applications, right? Like you do want to enable real-time proving. That is just a huge unlock. We could put more of our off-chain components into the zkVM that we currently can't, right? We cannot feasibly prove block execution of the EVM. I don't think it's far.
Yeah, it's not super far off. We got Snarkify in the crowd, or they were earlier. They're trying to get to real-time proving by June, which is really awesome.
Yeah, we have this question: how do you address trust assumptions in the zkVM? I don't think we really jumped into this. This can be interesting.
This is an interesting question. I don't really know how to answer it, but I'll jump into a few of them. Really, let's see. There's a number of places in which you need to make sure you design your protocol right so that you don't have trust assumptions. This is one of the things that I'm thinking about. And I mentioned earlier in Steel that you could say, in our zkVM, you could query 1 million accounts like I was describing earlier, check their token balances, compute over them. But what happens if that RPC was malicious, right? Like you actually were computing over data that's not sort of actually true or real. And so that's where, in Steel, we call them Steel commitments. It's really important that you actually commit to a block in which that data was true. And we check that commitment when we verify the proof on chain. You basically have no guarantees of security if you don't do that, because you just might be computing over totally false information. So there's little tricks like that. And this, again, is one of those hurdles where, sort of programming in this paradigm, making sure that you're doing it in a way that's safe is a little bit more nuanced and takes some time to learn. Another place in which there could potentially be trust assumptions is actually in the trusted setup of the proof system itself. Our zkVM runs on we call it Zero Stark, our Stark-based proof system. Starks don't require trusted setups if you're familiar with ZK systems. But Starks are also really big. I think our Starks are about, I think it's 200 to 300 kilobytes in size. It would cost millions and millions of gas to verify them on chain. So it's not really feasible to. And so what most teams are doing who are taking a similar approach is like, you actually take the Stark and you verify it inside of a small like Grot16 snark or a Plonk snark, which, so you actually like write a ZK circuit that verifies the Stark. And in doing so, this ZK circuit sort of just compresses that proof. We call it Stark to Snark in our system. And so we have a Circom circuit, and we can use through Grot16 or Plonk sort of generate a proof of that. And that proof system, that Snark system, does require a trusted setup. And so making sure that you've done that trusted setup in a way that's verifiable, reproducible, transparent, etc. I think we're the only zkVM team that has done a public trusted setup. There are other zkVMs, at least I'm thinking of one of them that has, done a private trusted setup, but it's not verifiable or reproducible in that way. And so that's a really key characteristic as well, is to ensure that, somebody didn't do a trusted setup in such a way where, there could be a vulnerability in the future. I guess the last one that I'll mention that's kind of tricky and you wouldn't think of out of the box is, you've written a zkVM program, you've written this in Rust. How do you verify on chain that you're actually running the right program? Right, is also another place in which if you don't design your system properly, you can have some issues. So a good example is like, maybe I write some malicious program that is calculating fees in a way that favors me as the protocol operator. And so like, how do you know that the fee is actually 1% or 0.5% before you process a transaction? And the way that we solve this is, you can actually compile a zkVM program and get something like a smart contract address. We call them, what is it? program IDs. It's like a universal, or excuse me, a unique identifier for your individual program. And in order for that identifier to be reproducible, you really have to have great compiler technology. Like in this case, for example, the Rust compiler introduces file paths into the build process. So if you just like rebuilt this program, you write a program in Rust and you rebuild it 2 or 3 times, you get a different unique identifier. And so in this case, we run the compiling inside of Docker to sort of eliminate that variability and generate this unique program ID. That program ID then gets set in a smart contract so that you know that that smart contract is only ever running that zkVM program and not any other one.
Those are pretty cool. But that's what we don't have to worry about.
You don't have to worry about it anymore because we solved them. But that's 3 ways in which you might have trust assumptions had they not been solved. And then actually, just like anytime you're using ZK, you're assuming there's no soundness bug or in your proof system. That's the additional sort of code risk or trust assumption, is that this is a secure, sound proof system. Some protocols are going multi-prover. We've invested in order to mitigate that risk, right? You can check that 2 of 3 proof systems agree, just to ensure that if one of those systems had a soundness bug, you could prevent attacks against it. Sort of almost like in the same way that a multi-sig works, this would be multi-proof. And we've certainly invested a ton into security and audits. We've never had such a significant bug, and there will be billions of dollars secured by our zkVM here quite soon. So yeah, I think that's it.
I think, yeah, last question is what's next. So from our side, more and more proofs, right? I think we are excited to push Malda out to market very soon, as we have finished the audit as of this week with someone pretty cool that you guys also use. Very nice. So that's exciting. But for the future, I think like our idea for future development is to put every single logic and operations into the zkVM and then only use the proofs on chain, which is, I think it's a great vision because it adds to Ethereum scaling like so much. but second of all, I think what we are also interested to explore in the future as it becomes feasible is to directly just use the Starks, right? Because we know that there is an improvement there in latency if we somehow remove that, and there are already tooling that enables applications to rely on only the Starks, but they are a little bit, I think, clunky. Native rollups can be a great way to use the Starks, but I think there are a couple of opportunities there. And right now we are happy with the latency. In the future, with larger proofs, with Starks, I think there is an incremental acceleration there when we can remove it, which is not yet feasible.
Yeah, Barnabas brings up a cool concept that I think is like really illustrative of where things are going with ZK. Is imagine that you can write your application logic not on any chain. Essentially, you write it in a zkVM program like this, and you just verify those proofs across any chain. And so this idea of a universal ZK application, something like that, I think is a really compelling and exciting idea. And this is really how we get to real world applications and more complex applications and logic. I think another thing for me that's coming up next and is really important is really just open markets for zero knowledge proofs. Today, if like you hear the cost of proving, people are just sort of, I don't want to, they're not being malicious, but like they're probably looking at their proving costs in AWS, or they're sort of cheating and they own their own hardware, and so they have this really low cost basis. There are no open markets for this sort of generic ZK based execution. And that means that price discovery doesn't exist today. It's really difficult to understand what actual costs are. And so in building Boundless, that's one of the things that I'm most excited about is we'll really see for the first time, enable price discovery over ZK proving. And it's going to be dramatically less expensive than it is today just by sort of creating an efficient and open market in that way. We're also developing a protocol called proof of verifiable work that will incentivize ZK provers. It's an incentive mechanism. It's not a consensus mechanism, but just in the same way that proof of work incentivizes, proof of work miners, proof of verifiable work will incentivize ZK miners to be producing these proofs. And so again, that'll dramatically reduce the costs and be a really effective subsidy to make sure there's, a really great and really endless supply of zero knowledge proving power to enable this next wave of rollups and ZeFi applications.
So last question, right? What does ZK powered DeFi mean to you? Like for me, it just unlocks all the TradFi use cases that we don't have yet on chain. One concept would be doing complex computations over a data lake. that we put somewhere, and we could potentially get to the stage where people can actually take a loan to buy a house, but everything would be happening in a verified setup, right? Like not everything will happen on chain. Part of it will happen off chain, but you verify it, and you can actually run the risk analysis that is needed. While in Solidity, you can increase the TPS as much as you want. It's just the constraints of the system. I don't think you can get there, and I don't think you need to get there.
Yeah, exactly. I think that's where we're going to, is where you really chains become settlement layers, right? They sequence and settle state updates, and really a lot of execution moves off chain into ZK, and either through sort of a ZK coprocessor setup, kind of like the way that the Malda team is using our zkVM, or through some sort of dedicated rollup. Like for example, Hashflow has built what they call a verifiable exchange. It's the characteristics and performance of an off-chain centralized exchange, but with zero knowledge proofs of every swap and exchange. So they get this really nice balance of verifiability and high performance. And why do we work on blockchains? I think verifiability is really the key component. You know nobody did a double spend. You can check the state of the ledger yourself. That verifiability is a really key component, and ZK provides that as well. So yeah, I think that's a good way to put it, is sort of TradFi performance, Web2 performance, and costs ideally as well. Cool. I think that's it.
That's it. Yeah, we have time, I think, for questions, if there are any.
Does anybody have a question?
Well, ZK answers everything. Boundless answers everything.
No questions. All right, cool. Thanks everybody for your time.
Thank you.